So limiting reactant has a lot of applications in chemistry. This is one of those things, if you talk about industrial companies and chemical companies, they really are going to look at limiting reactants and percent yield. So a limiting reactant is the reactant that is used up first. So it's the reactant used up first. It's going to run out first, and it is going to stop the reaction. So if you think about your car, one of the main things that your car needs is gas. If you run out of gas, your car will stop moving. Your gas is usually your limiting reactant in your car. Every reaction has a limiting reactant, because if it didn't, it would just go away. The reaction would just go on and on and on and on and on forever. Actual yield is the amount of product. Yield is always going to talk about product. It's the amount of product. And I'm going to use the word actually, and you're not really supposed to do that in a definition, but that's the best way to describe it. Amount of product actually produced during the reaction. So then theoretical yield is the amount of product that should be produced. So if you think about theoretical, that means like in a perfect world, if everything goes perfectly, the reaction goes really, really well. This is the maximum amount. So you can think of that as well. It's the maximum amount of product that can be formed. And the actual yield is when you actually do the experiment or do the reaction, that's how much you really get. Percent yield tells you the efficiency of an experiment or a process or anything you're talking about, a chemical reaction or a chemical change. It's going to tell you how efficient it was. And the formula for percent yield is actually pretty easy to remember because it's in alphabetical order. So it's going to be the actual yield over the theoretical yield times 100. It is going to be, in alphabetical order, like I said, it's going to be a percent. One note, actual yield has to be given to you in a problem because it's measured. Theoretical yield is what you're going to calculate. So just keep that in mind. So when we look at this first problem here, notice I gave you the equation balanced. You will have them balanced. I'm going to read it, make a couple notes, and I want you to look at what the difference is between the stoic problems we were doing before. It says, what volume of hydrogen in STP? So what I'm looking for here is I'm looking for the amount of liters of hydrogen produced from the reaction of 50 grams of magnesium and 75 grams of HCl. So there's going to be a difference you should notice. 50 grams and 75 grams, how many liters? The difference is with stoic, you were only given one amount, and so you automatically knew that's where you started with. In these problems, you're given two reactant amounts, so you don't know where to start. So that's the difference between this and stoic. In stoic, you would only be given one amount, and you would just convert it until you got to the liters. In a limiting reactant, you're going to have two reactant amounts. You have to figure out which one's going to run out first. And the key to that is this ratio here given by the coefficients. A 2 in front of the HCl means that for every 1 mole of magnesium, you need 2 moles of HCl. You need double the amount of HCl. So to determine the limiting reactant, to determine which one runs out first, you have to figure out, do you have double the amount of HCl? So the way you're going to do that is you're first going to take your gram amounts, and you're very easily going to turn them to moles. And the reason why you're going to do that is when you look at the balanced equation, the 1 and the 2, the coefficient in front, that's a mole. So you can't compare grams to mole amounts. You have to have them in the same unit. So I'm going to take my grams and I'm going to turn them to moles very simply by dividing by the molar mass. So magnesium is just a single element. So I'm going to get 2.0568 moles of Mg. Might be good to take these to a few more decimal points than you would for your answer, just because you're going to have to compare things. Then again, I'm going to do the molar mass of HCl, 36.46, and I should get 2.0570 moles of HCl. So when you look at this very quickly, they're about equal. So you can't say, oh, they're equal, there is no limiting, none runs out, etc. and so forth. You have to take it a step further. You have to look and you have to say, in this problem, according to the balanced equation, you need to have twice as much HCl. For every 1 mole of Mg, you need 2 moles of HCl. So what you're going to look at here is, if I have 1 mole of Mg, I would need 2 moles of HCl. So if I have around 2 moles of Mg, well, double that should be 4. So in order to have that be in the right proportion, I should have 4 moles of HCl. I only have 2. So automatically I don't have enough HCl. Remember, you need double the amount of HCl. 2.0570 is not double 2.0568. So that means the HCl is the limiting reactant. So you'd write HCl is LR. Might be a good idea to box that off so I can see that you know that. And here's why you need to know that. That then becomes the stoich. So remember, in stoich, you're given one number. You do the whole, grams to mole ratio to grams. Here, you're going to start with the limiting reactant. That is your starting point. So the point of finding the limiting reactant is to figure out which reactant to use in the problem. So because HCl is the limiting, that's what I'm going to do. We've already turned it to moles, so you don't have to go back and do that again. So with these problems, what you can actually do is start right with the moles, and you're getting theoretical yield. It's a stoich. It's just a stoich problem. So I'm in moles already. I need to change substances. So I do moles over moles, HCl on the bottom so I can cross it out. What I'm looking for, and I made a little note, H2 goes on the top, and just like the stoich, the numbers come from the coefficient, and then the answer is asking for liters. So then I just take my moles, and then I do 22.4 liters. So this right here is exactly like the stoich we've been doing. The only difference is, usually I would do grams to moles first. Well, I already know the moles, so I just go right to the mole to mole ratio. So then you go ahead and calculate that, and you should get about 23.04 liters of H2. So again, the reason you calculate the limiting reactant, you know where to start when you do the stoich to figure out the theoretical yield. So we'll do a couple more here. Silver nitrate and sodium phosphate are reacted in equal amounts of 200 grams each. So you have each 200 grams here. How many grams of silver phosphate are produced? So again, the difference is you have 2 amounts. You have to figure out which one to use. The only way to do that is to do the limiting reactant. So I'm going to take my 200 grams of each thing, and I'm going to turn them to moles so I can compare it to the mole ratio in the problem. That's why I'm doing this. So I can compare it to the mole ratio that's shown with the coefficients. So I'm going to have 1.177 moles of AgNO3. I'm going to do the same thing with the Na3PO4. Molar mass on the bottom. And I'm going to have 1.22 moles of Na3PO4. So now I have mole amounts. I'm going to go back to my equation and say, okay, the ratio is 3 to 1. For every 1 mole of Na3PO4, I need 3 moles of AgNO3. So now I'm going to look real quick. Okay, the 1, Na3PO4. I have about 1. You can round that to 1, or you can really do the number, 1.22. But I know if I have 1 of these, I need to have 3 times as much as this. So if I round this to 1, and I multiply by 3, that means I should have at least 3 moles of the AgNO3. I do not have anywhere close to that. I have 1.1. So again, if I have 1 mole of this, I need 3 times as much AgNO3. I have around 1 mole here. I need probably around 3 moles. I don't have anything close to that. So that means I know that the AgNO3 is the limiting reactant. Another way you could do that is simply by dividing them. So if you know that the ratio is 3 to 1, what you can do is take the AgNO3 amount, 1.17, and divide it. by the Na3PO4 amount. And what you're going to get is 0.96 to 1. These need to be relatively close, and you see this is so much less. So again, that's why AgNO3 is the limiting reactant. Now that you know the limiting, that's where you're going to start when you do your stoich. So I have 1.177 moles of AgNO3. And now it just becomes stoich. I'm in moles, so my next step is a mole to mole ratio. Moles of AgNO3 goes on the bottom, so I can cross it out. What I'm looking for, Ag3PO4 goes on the top. That's why this is helpful up here. Coefficients tell you what to put in front of the moles. And this particular problem is asking for grams. So I'm going to do 1 mole of Ag3PO4 on the bottom, and then the molar mass of Ag3PO4 on the top. Again, if you get confused by that, they should match. Whatever compound you have here, whatever formula, the molar mass of that should be on the top. So I'm just going to go through and do my math here, and I get 164.22 grams. So now we're going to change it up a little bit, and you're going to have one more thing to do here. So read your problem. Aluminum hydroxide is often present in antacids to neutralize stomach acid. If 14 grams of aluminum hydroxide is present, determine the theoretical yield of aluminum chloride. So that's what it's talking about when the tablet reacts with stomach acid. If the actual yield is 22 grams. So remember I told you the actual will always be given in the problem. And right there it gave it to you. It says it plain as day. The actual yield is 22 grams. What is the percent yield? So this is actually a percent yield problem. And if you remember your percent yield equation, it is going to be the actual yield over the theoretical yield times 100. You have the actual yield. It's right there. They gave it to you. So what you need to find, what you need to calculate is the theoretical yield of aluminum chloride, as it said. Determine the theoretical yield of aluminum chloride. Now, this is a little bit different from the ones we did previously. You're only given one thing again. We're back to the stoich. So this kind of saves you time. You only have to figure out which one's limiting if you're given 2 reactant amounts. Here you're only given 1 reactant amount. That is automatically the limiting reactant. So that is where you're going to start. So I'm going to do 14 grams of AlOH3. Now it becomes a straight stoich, normal stoich, to find the theoretical yield of aluminum chloride. So I'm going to go grams to moles. Molar mass of AlOH3 goes on the bottom. Remember, it has to match. So whatever formula you have on the top, the molar mass of that should match on the bottom. I'm going to go ahead and cross that out. I'm in moles, so my next step is always a mole to mole conversion to switch substances. AlOH3 goes on the bottom so I could cross it out. What I'm looking for, AlCl3 goes on the top. Numbers come from coefficients. In this case, we just have all ones. And then whenever it says theoretical yield, it always means grams, just in case you're wondering. Very rarely it'll mean liters, but for the most part, it's going to mean grams. So I'm going to take 1 mole of AlCl3 and then the molar mass of AlCl3. 133.33. Now the one place where you can get confused is mass. You may be like, oh, isn't it the same? Remember, they need to match vertically. So the formula here has to be the molar mass here. The formula here has to be the molar mass here. They have to match up vertically. So I go through and do all that math, and I get 24.0 grams of AlCl3. This right here is my theoretical yield of AlCl3. That's how much I should get if everything goes perfect. So the last part of this problem is asking to calculate percent yield. I put the formula right on the top. The actual yield comes right from the problem. They have to give it to you. The theoretical yield we just calculated as 24. Don't forget to multiply by 100, and you should get 91.67%. Remember, theoretical percent yield is always going to be a percent. Okay, one last one is going to put everything we just learned together. So you have an equation here. It actually is balanced. All the coefficients are 1. It's important that you take notes because everything's going to be thrown at you here. So it says 50 grams of silver nitrate is mixed with 50 grams hydrochloric acid. So right away I notice I have 2 reactant amounts. I'm going to have to find the limiting reactant. A way precipitate silver chloride forms. The solution is collected and dried. The dry precipitate is measured to have a mass of 38.12 grams. So you might be like, what is that talking about? The precipitate is silver chloride. That's what you need to go back and read. The precipitate's identity is silver chloride. So what they're talking about here is silver chloride. So what they figured out is at the end, the silver chloride weighs 38.12 grams. This is the actual yield. The actual is going to be measured from an experiment. It's going to be given in the problem. That right there is the actual yield. It's asking for the theoretical yield and percent yield of aluminum chloride because that's what it's referring to in the problem. So some of this you may have to go back and read the problem a couple times to really figure out what it wants. Now this is asking you to do everything we just learned. So we're going to start by finding the limiting reactant because I'm given 2 gram amounts in the reactants. So I'm taking those grams and I'm just turning them to moles. That's my first step. So I'm dividing by their molar masses, and I'm getting mole amounts. So I have 50 grams of each. And I have 1.37 moles of HCl. So again, I'm going to look at my problem. In this case, it's all ones, 1, 1, 1. So they should be the same. So when that happens, it makes things even easier. If they should be the same, you just pick the lowest. So if they should be equal, this should be 1.37. Well, this should be 1.37. This should be 0.29. This should be 0.29. So what I want you to notice is, if we say, okay, they both should be 0.29. This one has 0.29. This one has more than you need. You go the opposite way. This is 1.37. This should be 1.37. You don't have enough. So it's whatever one you don't have enough of is going to be your limiting reactant. Especially when the ratio is 1 to 1, that's pretty simple to figure out. Once I have my limiting reactant, my next step is always to figure out the theoretical yield. In this problem, it's talking about silver chloride. I'm going to start with my limiting reactant. That's why we even did that, because that's where you have to start. So 0.29 moles of AgNO3. Now it becomes a stoich problem to figure out the theoretical yield. I skipped a step where I already did the grams to moles, so I'm going to do a mole over mole ratio. AgNO3 goes on the bottom, so I can cross that out. What I'm looking for, AgCl goes on the top. Numbers come from the coefficients. They're all just ones here. And remember, theoretical yield, 99% of the time, is going to be in grams. So I'm going to do moles of AgCl on the bottom. And the molar mass, 143.32 on the top. And this is going to give me my theoretical yield, 41.56 grams of AgCl. Right there is my theoretical yield. In a perfect world, that's how much I should get. And then finally, the percent yield, remember alphabetical, is always going to be actual over theoretical times 100. So what you're going to do, the actual, again, given in the problem, is going to be 38.12. That will always, 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 always be given in the problem. 41.56, divide and multiply by 100, and I get 91.72%, which since that's so high, tells me that this reaction was very efficient.